Hi there. What you're looking at over here are two classification reports from two different algorithms. Let's call this algorithm A, and let's go ahead and call this algorithm B. But they're both trained on the same data, and then they're also evaluated on the same data. And we have some numbers here that allows us to compare two approaches. And when you squint your eyes a little bit, the numbers seem roughly the same. There's a slightly higher precision here, there's a slightly higher recall there. And when I look at the accuracy, there is a difference, but the difference is not necessarily night and day. It's a bit subtle. There's like a 2% difference between these numbers. Now, the interesting thing here is that if I were to judge which models are appropriate for production and have interesting properties, then I would say that there's actually a difference between both of these models that is kind of night and day, that doesn't really translate well into any of the metrics that you see. And you might be tempted to think that both of these two models have similar qualities, simply because these numbers are similar. So what I would like to do in this video is just highlight a aspect of classification models that you shouldn't forget when you're trying to compare models. And in particular, we're going to highlight how, although these metrics are super useful, they tend not to tell the entire story. So just to paint the picture, let's assume that we are dealing with an estimator, that's a classifier, and we're interested in figuring out if it has properties that we like. Then the first order of business is to make some predictions with some new data that comes in. This will give us our predicted values, and you can of course make metrics, and you can confirm whether or not these predicted values match the values that were actually happening, and you can come up with all sorts of metrics here. But let's now consider a different use case. Maybe you're not just interested in making a prediction, maybe you also want to do something with confidence. And for that, you would typically go for this other method on estimators, Probl. And in this case, you wouldn't get an array of numbers with labels. In this case, you would get an array of confidence values, I guess you could say. The hope, of course, is that these values sum up to 1 and that they also carry some sort of a interpretability. You want to be able to say something about the confidence of a prediction here. But that gives us a interpretability hint in what we would like to have here. Whenever we predict 0.9 as the confidence for a positive label, then we would also kind of expect that 90% of the time, it would actually be the positive class. Imagine that we would make 1,000 predictions and that all of these 1,000 predictions would have a confidence value of 0.9. Then it would be kind of odd if 800 of these 1,000 original examples belong to the positive class. That would suggest that we aren't able to interpret our model the way we like. And a key word here is that it feels like the model is maybe not calibrated properly. Observe here, by the way, that this is not something that we're typically capturing with metrics that are in the classification report. And in this particular case, I might also argue that it's a little bit easier to get an idea of how well the model is calibrated by looking at a chart instead. So let's assume that we've got a chart over here, and we've got an x and y axis, they both start at 0 and 1. And let's then say that on the x-axis over here, we are talking about predictions, and on the y-axis over here, we're talking a little bit more about what is actually happening. And let's assume that we're going to be doing some binning. So let's say there's this region over here between 0.9 and 1, let's say. What we could do is we can have a look at our test set. We can have a look at all the numbers that fall into this bucket, and then we can say what percentage actually contains the true class. So to highlight the example that I mentioned earlier, let's say between 0.9 and 0.1, we have 1,000 examples, and 800 of them were positive. Then I can come up with some sort of point in the middle here that represents this chunk of data, and I would have to come up with some sort of space over here, 0.8, and I can draw a dot over here to indicate that this bucket had this true probability rate for the positive class. And I can do that for all sorts of buckets that I define over here. And what you, of course, are hoping for is that if we are dealing with a very proper calibrated model, that all of these points would be exactly on the diagonal over here. That would effectively mean that the numbers that we get out of our Probl method are interpretable as a probability. In reality, though, if you were to draw all these dots and connect them together, you are probably not going to get a line that fits that diagonal perfectly. But what you do hope is that you don't deviate too much of it either. If you were to draw up something like this, for example, then I hope it's clear that even if this red line over here has a higher accuracy, that then for production reasons, this might still be preferable. There's a big interpretability win over here if you have a well-calibrated model. And with this little bit of intuition out of the way now, let's now go back and actually look at some code that highlights this phenomenon. So let's explain the setup. I've got this make classification function from scikit-learn that just generates me an x and y pair that I can train machine learning models on for demo purposes. I've got my xtrain and test here because I'm using the train test split function, and effectively I'm just training two models. I've got my logistic regression, and I've got a naive Bayes classifier. At the beginning of the video, I showed you some classification summaries with some metrics, and these were the two models that I showed. So as far as the metrics were concerned, these two models actually performed relatively similarly. But if I were now to look at the calibration chart, which you can explore by importing this calibration display object from the calibration submodule, then what you can do is you can tell the display that there's an estimator, this one in particular. You can give it the x-test and y-test variables, and then there's some extra settings that I'll get into in a bit. But by just doing that, you suddenly get access to a calibration display. Again, we've got that perfect diagonal line here that ideally we'd be close to, but you can clearly see that that's actually not happening here. There's an area over here where the naive Bayes model tends to give lower probabilities than what's actually happening as far as positive class rates go, and here's the other way around. We are properly deviating from this diagonal over here. I can do the same thing for my logistic regression though. And when I look at that, oh my, it is a night and day difference. We are really close to the perfectly calibrated line over here. And you can easily imagine that this is an interesting property for a lot of use cases. Even if we ignore the accuracy numbers, this is a property that you'd be very interested in seeing. Now, before I wrap up this video, I do want to talk a little bit about the parameters that are involved in creating these charts, because it can be easy to come up with the wrong conclusion when you just look at these calibration charts. So for this next segment, I have set up this interactive environment over here, and let's explain how it works. I've generated a big train set, and from that I am training a estimator. That's a classifier, and I've got one for this naive Bayes model, and I've also got a logistic regression. Besides the train set, I also have a test set, and this test set is going to be used in this calibration chart, together with this estimator. Now, in everything that I'm about to show, the train set will remain the same, and therefore this estimator will also not change. But I do have this slider over here that allows me to set the size of the test set over here. I'm just taking a subset, but that will allow me to show you what the effect might be of having more or less data. Besides that, I've also got this other slider over here that allows me to set the prediction bins. As I mentioned earlier, we have lots of these buckets over here on the x-axis, and the number of them, that is something that I can configure as well. But the calibration chart also allows you to have different strategies for bucketing. What I'm drawing over here is a bit of a uniform distribution, where I draw uniformly over the x-axis over here, but you can also choose to use the quantile strategy instead. That's what's currently selected, and this will allow you to have these bins be determined by the distribution of the predictions that come out of this estimator over here. That's really dependent on those Probabl values that I mentioned earlier. Now, with that little explainer done, let's actually start playing around here. So one thing that I might do is I might just show less bins and see what that's like. Well, as you can see, if I have very few bins over here, and if I've set the quantile strategy, then in this particular case, you're going to see 2 points over here, 2 points over here at the extreme, and then everything in the middle here seems to be mostly interpolated. So in this particular case, it does feel like you gain a lot more granularity if you just increase the number of bins over here. When you do this, by the way, you will also notice that there's a little bit more of a calibration imbalance on this chart than on this one. But your experience of the chart can really depend on the number of bins that you've selected here. That's a thing to think about. Another observation, though, is that this bucketing strategy can also really make a difference. Let's set that to uniform now. And suddenly, you can see that all the dots that before were at the edges now kind of appear in the middle over here. In most cases, I would recommend using the quantile strategy, and there's also a reason for it. If I think about how many data points are actually used for all of these dots over here, then I hope you can imagine that we have a lot more data being associated over here at this point in time than in the middle. If I were to change to the quantile strategy, you can see how this is just confirmed. There's a lot more density on the edges over here than in the middle. And that brings me to this final slider that I just want to show you, which will allow me to show you what happens if I have less data. So let's just go for a small number over here. Maybe have it be super small. And let's also go for uniform. Can you see how much it jumps around in both cases? Well, the primary reason for that is that some of these buckets that are denoted by a dot over here, they just barely have any data whatsoever. If I were to increase it, then you are going to notice that it gets better and better. But even in this case, it probably feels safer to turn on the quantile strategy, or alternatively to tune down the number of prediction bins. But even then, I do think that the quantile strategy tends to make a lot more sense. Also notice that if I were to increase the bins by a lot, then even in the quantile setting, you do have a little bit of risk that there's simply not a lot of data per bucket over here. And as a rule of thumb, you probably do want to have at least 30 data points per bucket. So, if at all possible, do try to make sure that whenever you're calibrating that you use as much data as you possibly can, because that ends up giving you a chart that's just easier to interpret in general. Another interesting experiment that you can do, by the way, is you can just play around with the number of data points that you throw at the calibration, which I'm doing over here. And what you're kind of hoping for is that at some point you have enough data such that the distribution doesn't really change as much anymore. And that definitely feels true when I have high numbers over here. But if I were to go for super low numbers over here, then you do see that it really can still jump around, even when I have the quantile bucketing strategy. Having said all of this, these are calibration charts, and they give a nice introduction into this whole field of calibration. And it's an important thing to keep in the back of your mind because in the end, you do want these probability features of your model to make sense. There's a lot of use cases that can't really be met if you end up having a classifier that doesn't really output something that can be interpreted as a probability measure.